Okay, so 20 of you have answered. Keep going as we go through this. So what do we call the line that traces the average shape, i.e. halfway between the upper and lower surface of an airfoil? Is it the chord, the leading edge, the trailing edge, or the camber line? 90% of you have said camber line, 5% of you have chord, 5% trailing edge, and 0% leading edge. Now, the interesting thing is last hour, no one had put trailing edge, and some people had put leading edge, and you've swapped. It's always interesting to see the slight differences. And 86% of you have the correct answer. It is the camber line. If we go back to our airfoil, we have our leading edge here, our trailing edge here, and those are, by definition, the leading edge is the first part of the airfoil that the flow sees, and the trailing edge is the last. The distance, pure linear distance between them, is our chord, which we use that little c symbol for. Now you may see a little c bar or a little c hat, and those are things like mean aerodynamic chord and mean structural chord. But for an airfoil, that's the same thing, so it doesn't matter. The camber line, which is generally curved, is that mean point between the upper and lower surface. It describes the shape of our airfoil. If the camber line is a straight line, what type of airfoil do we have? Yes? Symmetrical. We have a symmetric. If the camber line is curved like that, we have a standard positive camber airfoil. If it's curved the other way, it would be negative camber. Where might we use a negative cambered airfoil? Not necessarily on an aircraft. What application might you think a negative cambered airfoil might be used for? Yeah. Yeah, so the wings in Formula One and spoilers and stuff on sports cars, those are negatively cambered airfoils. I mean, the only difference is you just flipped a positively cambered airfoil upside down because we want to generate downforce. Okay? Now, we have many different types of airfoil, different descriptions. Some of the most famous are the NACA, or National Advisory Committee on Aeronautics, series of airfoils, and there's several of those. And each of those, what's nice about those is the numbering scheme for that airfoil, be it a 4-digit airfoil or a 5-digit or 6-series airfoil, describes both the shape of the airfoil, the curvature of the leading edge, the thickness of the airfoil, and the way it's cambered. So a 0012 is symmetric, 12% thick. That means its thickest point, it's 12% of the chord. A 2412 will be positively cambered, and that 20, the 2 and the 4 describe the location of maximum camber in distance of chord, in percent of chord, and the amount of camber. Other airfoils have more sophisticated things, but it fully describes it. Now, NACA aerofoils are the most commonly best known, but they're actually not used all that much. You know, Boeing, Airbus, they will all have their own airfoils that they design and use. And they'll have their own naming schemes for those airfoils. Okay. Okay. Question 2. What is the point on an airfoil where the moment coefficient is independent of the lift coefficient? Is it aerodynamic center, center of pressure, the leading edge or the trailing edge? I see some of you are still stuck on this leading edge bit. It is, I'll give it to you, the aerodynamic center. Anybody remember what center of pressure is on an airfoil? Yeah. Yeah, and what's special about center of pressure? Yeah. Yeah, that moment will be 0. The nice thing about the aerodynamic center is it doesn't move with angle of attack. It stays at one place. For low speed, roughly where is it located? as a fraction of chord? Yeah. Quarter chord. As we go faster, get closer to the speed of sound, it moves. Does anybody remember to where roughly it will migrate towards as we go faster? Yeah. Yeah, half chord. But in general, if I'm flying at a given Mach number, it stays at one place. I increase my angle of attack, I decrease my angle of attack, it stays at one place. The fact that it moves as we go faster causes some unique problems. It's what causes what's called Mach tuck, which is what happens is for conventional configuration aircraft, as we accelerate to closer to the speed of sound, say from Mach 0.2 up to 0.85, the aircraft goes out of trim. It wants to nose down and go into a dive, which of course means it goes faster, so it wants to do that more. That's why we have all-moving stabilizers on commercial transports. It's so we can trim out that tuck. And back in the early days of commercial jet aviation, the pilot had to do it by himself, and every once in a while, they would forget to do it, and the plane would go into a dive. And in some cases, the aircraft actually went supersonic. There was a case of a DC-8 that went supersonic because they didn't trim out the Mach tuck. Nowadays, we have more sophisticated systems that trim for that. What's called speed, stability, and trim, and they trim out Mach tuck and those other things. On Concorde, the problem of the aerodynamic center moving was so much more severe. Now, why do you think it would be more severe on Concorde than on, say, an A320 or a 787, other than it's going Mach 2? Why do you think naturally it would be more severe? What's different about about Concorde's configuration? As a delta wing, it doesn't have a what? It doesn't have a horizontal tail. So there's nothing to counter that. So what did Concorde do? Does anybody know what Concorde did to counter that Mach tuck, that problem?
Sir?
Yeah.
Sir, they literally took fuel from forward tanks and pumped it into a backward tank in order to change the center of gravity and enable the Concorde to fly.
Yeah. So they move fuel around to change the CG to retrim the aircraft. Now, anybody else think of what you could do instead on a delta wing aircraft to deal with that change? Say what the TU-144 did. Yeah, you can have canards. In the case of the TU-144, they use the canards for when the aerodynamic center moved forward to counter that, also for approach and all of that. And then at high speed, where it was aft, they retract them. They still move fuel around, just not as much as Concorde. In fact, the fuel pumps on Concorde were part of the safety critical flight control system. So it was same as the hydraulics to drive the elevons. That isn't the case for most commercial transports, which was a problem. If they all failed at Mach 2, you couldn't land. Okay? So, a little bit more on, oh, there we go, center of pressure and aerodynamic center. So the aerodynamic center stays. The center of pressure does not. It moves around. That's why we don't like it. So as we change the angle of attack, our aerodynamic center stays roughly at quarter chord, and the center of pressure moves fore and aft. For a wing or an aerofoil that's generating zero lift, but has a nose-down pitching moment, where will the center of pressure be located? Anyone? Anyone want to hazard a guess? Will it be forward or aft of the aerodynamic center? Remember, the wing is turning nose down, so it's rotating this way. It's not generating any lift. So where would the moment be zero? Fore or aft of the aerodynamic center? Yeah.
Fore.
Okay, so I zero moment here. No, they were generating no lift, right? So there's no pressure differential between the upper and lower surface anywhere on the wing, but we're still generating a nose-down pitching moment. So where would the center of pressure be? Where would the point where you would have to have lift, but no moment be? Yeah. No, because remember, aerodynamic center, wings rotating. So we're going to now go aft. But how far aft do we have to go? Lift is 0. A standard, conventionally cambered airfoil generating 0 lift. It's 0 lift angle of attack, has a nose-down pitching moment. The aerodynamic center is now infinitely far aft of the wing. If it's generating a nose-up pitching moment, it has to be infinitely far forward. So it doesn't even have to be on the airfoil. That's why we don't like it. We don't use it in day-to-day parlance. Would be nice. It's a nice thing. It's always nice where we just deal with pure forces, but that's not always possible. Okay? Which properties are true for symmetric airfoils? They work equally well, upside down. The aerodynamic center and the center of pressure are co-located. They have no pitching moment. They produce lift at 0 angle of attack, and they don't stall. Well, it's nice to see that no one put they don't stall because airfoils stall. To get something that doesn't stall, you need more complex interactions. They work equally well upside down. Remember, they are the same. I flip it over, it looks exactly the same. So it works equally well. Maybe not very well at all in the absolute sense, but equally well upside down. What's nice about a symmetric airfoil? What type of pitching moment does it produce? Produce a nose up, a nose down, or none at all? Yeah. Symmetric airfoils produce no pitching moment. And as such, they produce no pitching moment. That means the pitch for any angle of attack within reason, not near stall, but any non-stall region. That means the pitching moment doesn't change with angle of attack. So by definition, it's 0 at 0 lift. It's at a CL of 1. It's also 0. Of 0.5, it's also 0. That means the aerodynamic center and the center of pressure are co-located. Here is one aerofoil where the center of pressure doesn't move for reasonable angles of attack. Because it produces no pitching moment, where might we want to use a symmetric airfoil? What type of part of an aircraft would it be really good for? Vertical tail, absolutely. Because on a vertical tail, for most of the operation, we don't want it to generate a whole lot of lift. I mean, we have to deal with the symmetries due to what's called P factor on props and stuff, but ideally we don't, and we don't want it to generate a moment at the same time. We don't want it to be turning the aircraft. On smaller aircraft, we tend to use it for the horizontal tail too, but on big aircraft like A320s, 737s, we actually do use cambered airfoils a lot of times. They're not fully symmetric. So it has no pitching moment and the like. It does not produce lift at 0 angle of attack. That is a cambered airfoil. Okay. Question 4. A normal cambered airfoil has what type of pitching moment? Nose up, nose down, or none? And it's good to see this time around that 52% of you said nose down because you still get it wrong, or nose up. So nose down. So I've got that camber line again. So we'll look at a cambered airfoil here. See if it works. So my camber line, imagine that. It's arcing upwards. That curvature is showing where we're generating lift. And if we look at these airfoils, here's quarter chord. Is there more curvature forward or aft of the quarter chord? It's easier to see in the one above it. There's more curvature aft. There's just more space aft. So it's going to be nose down. So cambered, standard, positively cambered airfoils produce a nose down pitching moment. Okay? That means we have to correct for that. That's why we have a tail. right? They want to turn down. And then the center of gravity is also in front of the neutral point. It may be in front of the aerodynamic center for the airfoil or the wing, which means the lift wants to nose down. So we have to counter for it more. What's bad about nose down pitching moment? What type of aircraft or configuration of aircraft would you not want to nose down pitching moment out of your airfoil? We're using the tail to counter that. Where might you not want that? Well, gliders have tails. I mean, yeah, obviously, the less nose down pitching moment, the better because of efficiency. But where would it be really bad? Yeah. Yeah, a flying wing, an aircraft without a tail. Because you have to counter it in that airfoil. If you don't have, it's naturally cambered, you have to then counter it with, say, a flap at the wingtip, especially swept wings, things like that. Also means that the further forward your CG is, the worse it gets. So that creates this strange feedback loop that we don't want. Okay. Which properties are true of a supercritical airfoil? It has A, a higher critical Mach number, B, delays the onset of supersonic drag, C, lift generation is aft loaded, D, has less nose down pitching moment, and F, it has weaker shocks. So let's briefly go back to our aft loaded airfoil. Does anybody remember what they're also called? What the other name for an aft loaded airfoil is? There's two other names for them. Supercritical airfoil. Anybody know the other name? Named after the person that first described them. They're also known as Whitcomb airfoils. Not expecting you to remember that last bit. But aft-loaded and supercritical are the same thing. So that tells us part of what it is. That's an airfoil designed to operate supercritical. Anybody remember what critical means in this respect? Yes. And what's the critical Mach number? No looking it up. When we're talking of Mach number, the critical Mach number is the free stream Mach number, as in far upstream of the aircraft, the speed the aircraft's flying, where flow over the wing or over the body will go supersonic. It will be critical. Supersonic, subsonic is subcritical, supersonic is supercritical. Critical is Mach 1. So this is an airfoil designed to operate above its critical Mach number. That doesn't mean it has a higher critical Mach number. For the same thickness and the same net camber, the critical Mach number will be the same. Maybe it's Mach 0.72. But what's different is by shaping our wing, or our airfoil, we can change the behavior after we go above critical Mach number. So what happens is flow goes supersonic over the top of the wing or over the top of the aircraft is it has to go back to subsonic. Why does it have to go back to subsonic? If the flow is subsonic coming in, why does it have to be subsonic going out? It's rejoining the free stream. If it's not subsonic, when it goes out and it was subsonic coming in, you'll get a pressure differential. A pressure differential over an infinitesimally small distance. That's called a shock wave. If it's over a larger distance, where we have high pressure over there and low pressure over there, what do we get? Outside, it's not much today. Yeah. Yeah, you get wind, you get flow. So if over long distance you get flow, that equalizes it. Over a short distance, you get a shock wave, a bang. So it has to be slow. It has to be subsonic when it comes off the wing. So let's look at supercritical. As I said, they're aft loaded, and I'm doing this wrong. There we go. So these are supercritical airfoils. What we've done is we flattened the upper and lower surface at the leading edge, meaning the flow accelerates and then decelerates more slowly. That means when it finally has to drop from supersonic to subsonic, it does that for smallest step change possible. So if it goes from Mach, say, 1.5 to Mach 0.8, that's a big step. But if it goes from 1.01 to 0.9 and then goes down to 0.8, that's a much smaller step. That means we get weaker shocks, which means for the same free stream Mach number, we get less drag. So what happens is those shocks develop, they get stronger, our drag goes up exponentially, and we want to delay that. To do that, someone trying to join, we put our curvature at the very end, the last possible moment. By doing that, that means we generate more lift back here. They're aft loaded. It also means what about our pitching moment? If we're generating more lift back here, what's it doing to our pitching moment? Yeah.
It's taking the pitching moment and moving it further out.
It doesn't move the pitching moment. Moments don't move on their own. What's the pitching moment at our aerodynamic center? Is it going to be more nose up or more nose down? More nose down. So aft-loaded airfoils, one of the downsides is they have more nose down pitching moment that we have to counter. Okay? So if we go back to our thing, they have the same critical Mach number for the same general shape. Their lift generation is aft-loaded. The supersonic drag is delayed. They develop weaker shocks, but they have a stronger nose-down pitching moment. Okay, before we move on from this, we talked about nose-down pitching moment. We talked about not wanting it. Anybody remember what type of airfoil we can have that will generate lift at zero angle of attack, so it's overall positively cambered, but we can cancel out that pitching moment? Anybody remember what that type of airfoil is called? Yes? Yeah, so it's our reflex camber airfoil. So we have this positive camber here, generates net lift. We have a little bit of negative or reflex camber at the trailing edge, which generates a small amount of downforce, but because of the distance aft of our aerodynamic center, cancels it out. We tend to use those things on flying wings. Now we have two ways of doing that. We can build it into the shape of the airfoil as you see here, or we can use small deflections of control surfaces, or a combination thereof. And that's what we typically use to do that. Okay? Okay. So that's poll one. Any questions at this time? How much do each quiz we have taken weigh for our final grade? So the quizzes during the semester are overall 50%, 15 and 15 for the two activity quizzes, and 20 for the midterm. And the final exam is 50%. Okay? Let's open up our wing. So everything we've talked about so far, wrong one, is about 2D airfoils. We're now going to move into the realm of 3D. So we're going to talk about what's different about wings and the other things we have to consider. Now, aircraft have wings. Rotorcraft have wings. We call them rotor blades. Where on, say, a commercial transport, do we have something that approximates a 2D airfoil? It's bounded. It doesn't have an open end. There's a wall at both ends. Anybody know? They go around, they spin. Yeah. Yeah, the blades in a turbofan. More so the stuff in a compressor and turbine where they're not tapered. They're airfoils, and they behave much more like airfoils. They have that wall. Turns out, like fan blades, because they're not what's called shrouded blades, they have an outer duct. You can get gaps, and so they have quasi 3D 2D effects, but the more internal stuff tend not to do that. They run in a groove and therefore are 2D in nature. But we're going to be talking about external wings for the next little bit. Answer survey, and we'll continue. Okay. So, quick question in case you don't. The lift curve slope is how much the CL changes for a given increment in angle of attack. So, if I go up by 1 degree in angle of attack, how much my CL changes. Or actually, it's in radians. So, if I go up by pi over 8 radians, how much does my CL change? So for a 2D wing, it is 2 pi alpha in radians is the theoretical lift curve. For a 2D thin airfoil, sorry, 2 pi alpha. So first question is it greater, for a 3D, is it greater or less than that? Okay, we'll start, and you can keep answering if you want. So, the lift curve slope of a 3D wing is greater than that of a 2D aerofoil. True or false? Ooh, we're at 50-50. Someone going to break that? And the answer is 51. False. The thing about 3D wings is they make life worse. Everything about 3D is worse than 2D. 2D is ideal. You can only do worse than ideal. The wingtip causes all sorts of flow phenomena that changes that relationship. And especially at low aspect ratio wings, we definitely get a lower lift curve slope. So that means for the same increment in alpha, we don't get as much CL. Okay? It also means we get drag and other properties and the like. Okay. A normal wing produces lift at its tip. True or false? And 67% of you kindly said false. So let's look at our 2D wing or 3D wing. There we go. It produces no lift at the tip. In fact, that's one of the requirements of being in 3D. Why does it produce no lift at the tip? Why can we say that with certainty? So, you're right. To get that lift, one of the characteristics is we have to have a pressure differential. The pressure has to be lower on the upper surface than on the lower surface. That's how we resolve those forces, right? If they're the same, you put them all together, add them up, the sum is 0, you have no lift. If there is pressure, higher pressure at the lower surface than the upper surface, two things must happen. It must either equalize via flow, i.e. those tip vortices, or you must get a shock wave. Again, to get a shock wave, the flow has to be traveling faster than the speed of sound. The flow above and below the wing, tip, external, is not relative to each other faster than the speed of sound. It has to go to 0. How it goes to 0 makes all the difference in the world. The smoother that curve, the more eccentric that ellipse is, that shape, the less differential you have incrementally as you go spanwise. The weaker those tip vortices are, the less induced drag you get. So this term induced drag is the drag induced by the generation of lift on a 3D wing. Now, what are the tricks that we can do to minimize that, to make that spanwise lift distribution? What can we do to our wing? We can increase the length of our wing so that each bit of that wing spanwise generates less lift overall. That's called the aspect ratio. We can taper our wing that forces more of the lift to be generated inboard rather than outboard. You just have less area. We can also do other things to our wing, like change the shape of the wingtips. So that brings us on to question 3. Winglets approximate a higher aspect ratio wing. So a winglet is a non-planar addition to the wingtip. Most winglets go up. Believe it or not, a winglet that faces down is more efficient. Why do we not tend to put our winglets downward facing? Anybody have a thought on that? Yeah, they're more likely to hit the runway. That's why. Now, that doesn't mean we don't have downward facing winglets. The MD-11 had an upward and downward winglet. What other aircraft? Where else have we seen downward bits on the winglets? We tend to do more up just because of that. Yeah.
The 737
Both up and down.
and downward.
Yeah.
And some UAVs
Yep. It all just depends. But downward is more efficient, all else remaining equal, but more likely to get pranged, as they call it. So without which disadvantage? Does it not increase the span? Does it not increase the root bending moment? Or does it not decrease, or does it not decrease structural stability? 65% of you got put down doesn't increase span, which is absolutely correct. In fact, that's the primary reason we have winglets. We need to improve the efficiency of the wing, especially if an aircraft, say, was designed to operate originally a shorter distance, and due to changes in technology and efficiency now can fly longer, but we can't increase the wingspan. Why might we not be able to increase the wingspan of an aircraft? What might limit the maximum wingspan of an aircraft? You have obstructions around the runway. What might be even more limiting than obstructions around the runway? Especially for, say, not A380 sized aircraft, but say 737, A320. Yeah. Yeah, manufacturing, but operationally. Where do aircraft have to go every time they land? Yeah, they have to go on a stand, and stands are sized. An A320 and a 737 are what are known as code C. They fit in a specific box. If we make their wingspans just a little bit larger, they go in code D. All of those stands that they park next to each other, and there's not a lot of space, they now can't fit them in. A330, A350, 787, the original 747, they were code E. We make their wings a bit longer, they become code F, like an A380. Far fewer stands. In fact, fewer airports. Very few airports can accept an A380 on its own. Manchester is not a code F airport. It has code F taxi pathways and code F runways. But the A380 can't go everywhere. And if it has to go outside of where it's specifically allowed, it has to be escorted, and they have to make sure it doesn't run into things. So that's the main reason we don't want it. The other reason is by doing that same, instead of up, instead of out, we're not generating lift further away from the wing root. So we're not increasing the bending moment. Okay? Those are the really two primary advantages. Now, that being said, a 2-meter tall winglet gives you less lift-to-drag ratio benefit than a 2-meter wing extension. But it may be worth the trades. One of the other downsides is because I'm changing the angle, I now have interference between those two surfaces, those two components. And back when they first started doing winglets, it really made a difference. So when I first started working for Delta Airlines 26 years ago, 26 years ago, we had some 727s we had retrofitted with winglets. But because of the way we operated those 727s, yes, we flew them from Atlanta over to the West Coast, but a lot of our flights were shorter distance. It actually cost us fuel burn because of that interference drag. With the advancements of CFD, we were able to change that interface shape, and we got what are called blended winglets, and they became much more effective for those kind of aircraft that we use over a big range of different distances. But winglets are not the only option. So we'll talk about those more in just a second. One of the downsides of winglets is because of the way they relate, they make your wingtips want to twist back. They decrease the structural stability. So almost all aircraft with winglets, they put weight on the leading edge of the wingtip. Just chunks of tungsten. 30 years ago, they'd use spent uranium, depleted uranium, which is when you refine uranium, you get all this leftover U-238, which isn't particularly radioactive. You don't really have to worry about it, but they would use that. Okay? And then finally on this poll, to decrease the drag at high speed, which options are typically used? Do we typically sweep the wing, use aft-loaded airfoils, or decrease the thickness to chord? And this is a bit of a trick question because you can do a mixture of all three, and we do a mixture of all three. We use our supercritical airfoils. If you fly, next time you fly, if you fly in an air carrier where you have to board the aircraft via the stairs, and you board by the rear stairs, look at the underside of the wing at the trailing edge. And you'll see it on an A320 or 737, it'll have a fair amount of curvature. If you're flying a 787 or A350, it has a lot more curvature because they get more and more aft loaded. But we also decrease the thickness to chord because that's nice. We can get a little bit more. And all that aft loaded airfoils do is they allow us to increase the thickness to chord. We sweep the wing because that changes the incident Mach number because we're looking at the normal. So the cosine of the Mach number is we sweep it back. Now, why do we want thicker wings? What's nice about having thicker wings? They produce more lift at low speeds, so that's nice. What else is nice about having thicker wings? Especially in commercial transports. Yeah. Yep, they carry fuel, you have more volume for fuel. And the last reason we like thicker wings is they're lighter. Because for the same bending moment, you need less material. It's part of structures. When you use structures, that bending moment of inertia goes up, and so you get less stress in the members. So we like thicker wings, so that's why we tend to use slightly thicker wings now than we did 50 years ago, but they're aft-loaded, and we sleep them slightly less. Okay? We will close this one, see if there are any questions. Can you go through the last question on the midterm quiz, the one on escape velocity? We can in the future. Not all of you will have gotten that question. How do swept wing aircraft trim for pitch if they have no tail? Trim tanks as fuel are used. Some use trim tanks for fuel. The other ones will just trim with small reflex changes on the trailing edge. Now the challenge with that is that generates drag. So a tailless aircraft, we have a much smaller acceptable range of CG. And that's the thing. One of the other challenges, and we'll talk about it here when we talk about flaps, is has to do with high angles of attack and what happens as you go up in angles of attack. Where can we find past papers? I will make sure they're available. They're on, you'll see on the left-hand side of Blackboard once they're set up. How much do each quiz take away? We've done that. Okay. Last poll, and this one is on flaps and things. So ailerons are a form of flap, but this brings us into our terminology. A flap strictly is any surface or portion of a wing, leading or trailing edge, that we deflect up or down to change the local camber of the wing or airfoil. Okay? That is strictly what a flap is. So ailerons are flaps, elevators are flaps. You can have leading edge and trailing edge flaps. However, in colloquial parlance, when we are talking about aircraft and wings, we tend to say flaps specifically to trailing edge devices. So if we only use the word flap, that are there to increase lift and at the extreme increase drag. If it's on the leading edge and it's a flap, we call it a leading edge flap. If it does control, like roll control or pitch control, we will also call it something different. So if it's purely roll control, it's an aileron. If it's purely pitch control, it's an elevator. If it mixes roll and pitch, it's an elevon. If it mixes roll and lift, it's a flapperon. If it mixes pitch and lift, it's a flappavator. So we do it. So that's those colloquial terms. If it does both pitch and yaw, it's a ruddervator. So the V-tailed Bonanzas have ruddervators. But if so, in colloquial parlance, ailerons are truly a form of flap, but we won't refer to them as such. Gotta love that about our favorite thing. Okay? Next question. Which type of trailing edge flap increases the wing area. So now we're using it as a colloquial term. So this is, we want to generate more lift. Now when we talk about lift, we have a reference area, which is typically the planform area of our clean wing. That never changes. But we actually have to increase the wing area if we want to generate significantly more lift. So what type of flap do we use? Do we use a Fowler, a slotted, a plain, a split, or a Kruger? Now, a Kruger flap is a leading edge device, so we won't talk about that yet. We'll get back to that. All of the rest of these are devices that can happen at the trailing edge. A plain flap is just literally a hinge surface that goes up and down. Our aileron, our elevator, those are standard plain flaps. A split flap is literally where we split the wing in two. The bottom surface of the wing lowers down. Neither of those are going to change our wing area. All right? You'll see you don't see split flaps all that often. B-52s use them, some versions of the B-52. A slotted flap is a flap where as we deflect it, it opens up a gap between that and the main part of the wing. And that allows high pressure air from below the wing to come up over the top of the flap, which allows us to generate more lift without getting separation. A Fowler flap is a flap that translates. It's the one that you see moving aft. That's the one that increases our wing area. Now we can have combinations of flaps. In fact, most commercial transports have slotted Fowler flaps. They refer to them as single slotted or double slotted or triple slotted. It's how many gaps and how many surfaces you have. So if you watch, next time you're flying on a 737 or an A320 or an A380 or a 777, when they deploy the flaps, the first thing you notice is they tend to go aft before they start going down. They go down a little bit. That's the Fowler motion. The slot opens up, and then they go down to generate more CL through more camber. First thing they do is increase the wing area, then they increase the camber. If you're flying on a 787 or an A350, they don't move aft much. They don't have much Fowler motion. They just deflect down and open up that slot. So that's that type of thing. Okay. Next question. What type of leading edge device does not increase the angle of attack for stall? Now, one of the problems of increasing your camber is it decreases the angle of attack at which your wing stall, your airfoil, your wing stalls at. That's because we're doing more curvature, there's more likely to get separation. So any flap, leading edge or trailing edge, will decrease the angle of attack at stall. The only way we can recover that is through a slot. So anything with slots in it will increase or keep the leading edge, the angle of attack. Remember, Fowler and split flaps are trailing edge devices, so they're out. So of these, which one do you think is correct? Which one doesn't have slot in its name? Slat is just a slotted leading edge flap. Yeah. Yeah. Yeah, the Kruger flap. So the Kruger flap is a split flap on the leading edge. It drops down from the lower surface. And on older aircraft, 737s, 727s, even 747s, we use Kruger flaps. And the reason for that is aft-swept wings tend to stall at the tip first, which has two disadvantages. One, if one tip stalls before the other, what does the aircraft want to do? Roll. Two, because they stall first, they unload first, they generate less lift. That means as we go up an angle of attack, the aerodynamic center of our wing moves forward. Now that reduces the distance from the neutral point to our CG. It reduces our static margin. That means as we go up an angle of attack, it reduces the amount of force it takes to increase the angle of attack further. It also means the aircraft may not stall cleanly, it may just mush. So it doesn't pitch down when it stalls, because the inner wing hasn't stalled, which is a problem. Now, we have come up with different ways of solving that. On the A320, A350, the like, they have hard envelope protection. You just can't go above a certain angle of attack. And if the aircraft thinks you have, it just shoves the nose down. And if you're flying straight and level and the angle of attack sensors, two of them fail, and they say you're too high, the nose goes down, and hopefully you're up at 30,000 feet because you're going to lose 10 or 15,000 feet trying to correct. If you're at 5,000 feet, that's not a good thing. Or on 737 MAX, they did the MCAS addition to the speed trim system. Does the same thing instead of elevators, uses trim, and that went poorly. And as we all know, that was a bad outcome. But we do those things because of that mushiness. So at high angles of attack, we want the root to stall before the tip. So we put slats out at the tip. We put Kruger flaps at the root. And if you go out to a 737, you'll notice when the hydraulics are off, that the inboard inside of the wings, or the engines, the leading edge, they'll droop down. You'll actually see them. The Kruger flaps. Okay. Last question for today. Why do we use leading edge and trailing edge flaps? Is it to increase the maximum lift coefficient, increase the lift to drag ratio, increase drag, increase turn radius, or decrease field length? And it's those three. They increase the maximum lift coefficient. That's the primary reason. Unfortunately, as we increase maximum lift coefficient, we're going to generate more drag for each amount of lift, so that decreases our L over D. And that's the balance. For takeoff, we want as high L over D as possible. We want to be able to climb as quickly as possible, avoid running into that mountain or tree. But for landing, we need to get down and slow down. And especially with gas turbine jet engines where we have to generate thrust at all conditions, we need to increase drag. So the difference between takeoff and landing flaps isn't so much the maximum lift coefficient, it does go up, it's the amount of drag, how much we decrease the L over D. So it does increase drag in those conditions. Sometimes that's good, sometimes that's not, but the main reasons are decreased field length and increased maximum lift coefficient. Some aircraft, some fighter aircraft, they actually use flaps when maneuvering to get that lift coefficient up so they can pull a tighter turn, an instantaneous turn. Okay? Let's see. Are there any more questions? So the Kruger flap does not increase. No, the Kruger flap increases the overall camber, but doesn't increase the angle of attack at which it stalls. It actually decreases the angle of attack at which that portion of the wing will stall. That's why we use them on the inboard. Okay? Any other questions? Okay. I will see you next week. By the way, on Friday, you should be able to see the feedback for each of the quiz questions. If any of you don't have a mark, if you look and it says 0, look above it, and if it says needs marking, for some reason Blackboard has flagged your quiz that I have to review it. And it's usually because you ran over time, or it was late, or Blackboard just decided you were not the person it likes today, and I will clear those if you have any of those in the next day or so.